my name is Katie Lynn, and today I'm going to present on my research on making accelerators first-class citizens in the data center. An increasing number of data centers now include accelerators. Examples include Google's TPU, Microsoft's Catapult FPGAs, Amazon's F1 FPGAs, and there are many more examples. Big companies like Microsoft and Google are turning to specialized hardware in order to support their data center scale workloads. So the TPUs are used for TensorFlow machine learning processing, and Catapult is used for Bing machine learning models. We're also seeing accelerators being used more like distributed systems. So some data centers now offer accelerators which are networked together so they can communicate with each other directly without CPU intervention. Examples include Google TPU pods, Microsoft Catapult, and Facebook Xeon ASICs, which are used for machine learning training. The advantages of this type of system are similar to that of a distributed system of CPUs. You can do scale-up style computation where accelerators are aggregated to compute on larger workloads. For example, TPU pods aggregate TPUs for supporting larger machine learning models. You can also do scale-out style computation where each accelerator can be used for one copy of a job, and there are many copies of each job. In this case, the distributed systems model allows for more flexible allocation of resources, helping to prevent resource stranding. So if a node's CPU is being used for a different computation, the accelerator can still be used by a remote CPU. Finally, accelerators that communicate with each other directly can communicate at much higher bandwidth with lower latency. The question is, how should we integrate accelerators and represent them to the user if we want to use distributed accelerators as easily as we do distributed CPUs? Our ideal abstraction is hardware function as a service, which is similar to CPU function as a service, which is implemented in platforms such as Google Cloud Functions, Azure Functions, and Amazon Lambda. These providers allow you to upload code of a function, and then when you invoke the function, the provider's fast framework handles provisioning and scaling. Specifically, this is for scale-out style workloads. The nice features include the fact that the users specify what computation they want to run, but the framework handles provisioning and scaling. We would like this for accelerators. In this case, each accelerator is a function. So the user specifies what accelerator code to run, but doesn't have to deal with the provisioning of the accelerator instance, and the framework will automatically provision more instances if needed. My interests are if we're going to support this style of communication, what should the hardware on a node look like? Specifically, I've been looking at networking, what type of networking stack we should use. We've been looking at comparing two different designs. The first one is more often used. In this one, the CPU runs the network stack, which is nice because you can reuse existing hardware, mainly the CPU and the NIC, for networking. It's flexible and easy to modify because the network stack is just in software on the CPU. However, you're using CPU cycles that could be used for other computation, and the CPU is not the most efficient way to do packet processing, especially at high bandwidths. Finally, there's higher latency just to the fact that you have to traverse the PCIe bus when communicating with the accelerator. The second option, like Microsoft Catapult does, is to have an all-hardware path. In this case, you need additional hardware in order to implement your networking protocol, and because your networking protocol is in hardware, it's harder to change. However, your performance is more efficient and you have lower latency due to the tight coupling of your networking hardware with your accelerator. So we ask the question, which option is better? When would you want to make an all-hardware network stack? This depends both on application characteristics as well as the hardware costs. The current examples we have of these types of systems are mostly for machine learning, but we're interested in how you would generalize this for other applications. So we looked at application characteristics and hardware costs, and these include the costs to use CPU cores for network processing. So the main factors we looked at for application characteristics are required bandwidth, desired latency, and number of simultaneous flows. The main factors we identified that scale hardware costs depend on which type of stack you're using. So if you're using a software-based CPU stack, it mainly scales the cost based on the amount of bandwidth you need because that scales the number of cores you need. For an FPGA hardware network stack, the number of flows needed scales the number of BRAMs, which are needed for storing flow state, and we found BRAMs with a limiting resource when implementing on FPGA, so that's the main factor that scales the cost of the FPGA hardware stack. For ASIC, we found the main cost scaling comes from the size of deployment because it scales the price per chip. And this is due to the fact that ASIC costs are dominated by non-recurring engineering expenses, which get smaller with larger deployments. So our first step is using modeling to understand the trade-offs between these different factors. So our modeling data comes from two different sources. For software, on the CPU, we're using data from TAS, which is an open source high performance TCP stack. And this is similar to Google's Snap TCP stack, which is their high performance TCP stack. For hardware, we start with a design called Tonic, which provides the core logic for a 100 gigabit TCP stack. We then augmented this for end-to-end fast path TCP operation because they didn't support things like packet header assembly. For FPGA data, we then implemented this design on various UltraScale Plus FPGA parts, and for ASIC, we synthesized it in GlobalFoundries 14 nanometer. For software, the bandwidth is estimated from data in the task paper, and for hardware, we estimate the bandwidth by multiplying cycle time by a given packet size, since the hardware outputs one packet header every cycle. And the question we wanted to ask with our model is at what bandwidth does the hardware stack have a lower total cost of ownership versus the software stack? So here are some of our preliminary results for FPGA and ASIC. For FPGA, again, we're comparing versus the number of flows because that scales the number of VRAMs, which scales the price. For ASIC, we're comparing versus number of chips. These graphs show what we call break-even bandwidths. So above the line, all hardware stacks have better TCO, and below the line, the CPU stacks have better TCO. We calculate this by fixing a value for the hardware design, such as target number of flows or the size of the deployment, calculating the TCO of the FPGA or ASIC network stack implemented under those conditions, and then calculating the bandwidth we can support for that TCO on a CPU based on the number of CPU cores with an equivalent TCO. We get discontinuities in the curve just because we quantize CPU cores. So we say that you can't buy, for example, half a CPU core. So we find that the conditions that are most advantageous for FPGA are when you're doing small packets with a low number of flows. And at the smallest number of flows and the smallest packet size that we looked at, we found it can be better for TCO to use an FPGA network stack at bandwidths as low as around 32 gigabits per second. For ASIC, we found that larger deployments are better as expected. We see that the curve does begin to level out around 10,000 chips, and at this parameter, the break-even bandwidth is around 20 gigabits per second. So for our next steps, we want to implement a prototype platform on FPGA. So we want to integrate with an example accelerator. We're thinking something like video processing or machine learning, and then test end-to-end with another FPGA. I'm also working with a collaborator who's developing a functions as a service runtime system for these accelerators, so hopefully I'll be able to integrate my design with his work. Thank you.